Hi there, this is a first look at polar curves and polar coordinates generally. Now, you'll need your black calculator for this. The black calculator is very, very useful in terms of allowing you to see the polar curves and the polar points. But one thing I will say is that I'm going to try and do it as well using autograph, which is actually a better version of what you will see on your calculator. But get used to it. First of all, you'll need to press mode on your black calculator, and you'll need to go down to where it says func, and if it's you'll need to then move across to where it says polar, or it says pole actually, P-O-L, and that pole means polar, and we're going to learn to display graphs using polar coordinates rather than just what would be generally called Cartesian coordinates. Cartesian coordinates are so called because Descartes basically decided he was going to. So this is Descartes, who's a French mathematician, also a philosopher, but he decided he was going to define points to be, I don't know, 4 across and 3 up. And if you do that, you define that point, you kind of say, well, that point to there, really it's a triangle, isn't it? It's 4 across and 3 up. But of course, there are alternative ways to do it. One way is to talk about its angle and its length, and we notice the use of r and theta here. That's what we're going to use in this. And when you use r and theta, basically how far away it is from the origin, notice this is sometimes called the pole, and it's that the fact that we call it the pole is because of this idea that I suppose it's like the North Pole, and the North Pole has like a polar you talk about polar expeditions and stuff, and that's why that's called the polar curves, I suppose. So anyway, this is what we're going to look at in this lesson. This is a picture from the North Pole actually, so that there's the North Pole there. You might not look it, and it's imagine the Earth being drawn, and think of this as how far you'd have to travel to go from the North Pole in any direction down the globe. And interestingly, the equator is around here somewhere. I think this is the equator line, and it just shows you this actually goes beyond, because if you sat at the North Pole you wouldn't be able to see all this, obviously. Even if you were 100 miles above the Earth, you wouldn't be able to see it. You wouldn't be able to see beyond the curvature of the Earth. But here what it's showing you is all the way around, and this is what we call 0 degrees. This is 90 degrees. This is 180 degrees, and this is 270 degrees. Notice how this is defined to be an angle from this positive x-axis in the anti-clockwise direction, which is a bit weird, isn't it? Anti-clockwise, you wouldn't necessarily choose that. But nevertheless, that's what we do. And what we do is we basically say, well, any point on it, where is Britain? Believe it or not, Britain's over there. Britons are a bit rubbish, so let's pick on America. There they go. There's New York, something like that. I don't know exactly where it is, but that's New York. Now, you can see it's on an angle, which that looks to me to be an angle, I reckon that's 15 degrees for each of these. Yes, it is. So that's an angle of 285 degrees to get to there. So what you then need to know is not just the angle, you need to know how far it is. And I don't know how far that distance is from the North Pole, probably about 6,000 kilometers or something like this. But whatever, no, I don't think it'll be even that much, but let's say 3,000 kilometers. So whatever it is, you have these 2 points of information to get you from the North Pole to any point on the globe. You have to go in a straight line on that bearing of 285, roughly 3,000 kilometers. And that will get you to New York. I'm making it up, obviously. So what we're looking for then is a more general case than just looking at the globe. We're looking at any point, and this is what I was talking about just now. Let's imagine this is 4,3 again. And if this was Sokotoa, you just knowing that that's 4,3 would be enough to find r and theta. Now obviously this is Pythagoras really, so you could go, you know what, r squared equals 4 squared plus 3 squared. And it doesn't take much to realize the Pythagorean triple, therefore my r is 5. I could also work out using my, I don't know, I keep on getting this little badge up, using my knowledge of trigonometry, Sokotoa again. So I could work out my theta by saying, well, say I took sine theta. Sine theta is opposite over hypotenuse. So I could say sine of my theta is my opposite. Well, I've said this is, what did I say? This was 3 up, and this is 4 across. So this would be opposite, and this is 5, of course, as well. So opposite would be 3/5. And I could calculate theta. Or I suppose what I could also say, by the way, is I could do it more generally. It doesn't have to be 3, 4, 5 all the time. I could do it more generally. So I could just call this x, I suppose, and I could call this y. And I get some equations which are that x is r cos theta, which is what we had here if I'd rearranged it, or this next one would have been it. So y is r sine theta, and r squared is x squared plus y squared. So I want you to write these down. These are important equations we're going to use quite a lot, but not necessarily today, but they're going to come up loads and loads and loads. Be aware, and this might not sound obvious, but when you square root a number, obviously you can technically get a plus or a minus, but we are only concerned when r is positive. We think of r as being a distance away from the pole. So to consider this to be a negative distance seems a bit weird. So we only allow it to be positive, or of course it can be equal to 0 as well, i.e. no distance from the pole. But we're definitely not allowed to be negatively distanced from the pole. Again, notice this word pole meaning the origin when you're doing polar coordinates. And so we'll look at what's called the 2 pi convention. Now, 2 pi convention, basically, we could call this instead, if we wanted, this 360 degree notation convention. And it's where basically you start at 0. Now notice, if it was in degrees, it would be 0 degrees, or it could be in 0 rads as well. This is, you've got this choice, of course. This, of course, is 45 degrees. This is meant to say pi by 2, or 90 degrees. This is 135 degrees. And you can see it's just getting bigger and bigger and bigger. This one's 180 degrees. 5 pi by 4, if you do it, is 225 degrees. This is 270 degrees. 3 pi by 2. And this one is 315 degrees. And eventually, of course, you get back up to 360 degrees. But notice the way you define this to be, whether you use degrees or pi, radians, etc. This is the 2 pi convention. So all angles for this, theta has to lie between 0 and 2 pi. It can be equal to 0. It can't really be 2 pi because that's you're back where you started. So bear in mind that information we just had. This would be a question which would ask, and I expect you to indicate that you understand what is meant by these polar coordinates. So I've given you 2 polar coordinates here. I'm going to draw a picture. Let's see if I can draw a picture. You notice I've got a polar bear for you there. So the first one says it is, now I should point out, from now on we're going to talk about points. Any point now is going to be defined in terms of r, theta. Notice the r always comes first. This is the distance, followed by the angle. Next thing I want to just highlight is pi by 12, you should learn, is worth 15 degrees. So for instance, pi by 4, I know that's like 3/12. So this is 45 degrees. And the slightly horrible one is 23 pi over 12. But as soon as you know pi by 12 is 15, really it's 23 lots of 12. And what that actually is 345? That sounds about right to me. It's quite a big old angle. Anyway, so if we take that as read, so my 2 points, my point A says it's A to A and 20, and it's this angle. So I have to go A to A. Notice I'm suggesting it's down here, and that's because 345 is a big old angle. In fact, I reckon it's there. I'll make up the distance, that's 8. This, I reckon, must be, if you like, 15 degrees, or pi by 12. That's what's left over from a full turn. Obviously, I said it's 345. And this one, I reckon, it says 5 away, so let's draw it 5 away. And you'll notice I've drawn it 45 degrees. So if this is 45 degrees, you can see effectively I've got a little triangle here. And this is what this is all about. Now this point down here they said was A, and this is B, and this is the angle O. What are the 2 questions? It says find the distance AB. Now you might have already spotted really, this is the cosine rule. The cosine rule lets me find as long as I know that whole angle, and it's not hard to work out what it is, that whole angle, and I know these two distances, I know that's 5, I know that's 8. So I can write that AB squared equals, well, it's 5 squared plus 8 squared minus 2 times the 5 times the 8 times the angle in, cos of the angle in between. Now I could do it in degrees, I'm going to do it in radians. It's pi by 12 for that section, because I reckon that was what was left over from a whole turn, and pi by 4 for that section. So if you do that, pi by 4 is like 3 pi by 12 plus another pi by 12 is like 4 pi by 12 or pi by 3. So that's what I reckon that angle is if you add the two parts together. I'll need to chuck it in my calculator. So I'm typing it in now. What is it? It's 5 squared plus 8 squared minus 2 times 5 times 8 times cos of pi by 3. So you need to make sure you get that. Well, you know where that is in your calculator. I'm sure you do. And I get exactly 49. So it's obviously been designed, this question, to give nice numbers. That's 49. But notice that's AB squared, therefore AB must be 7. Doesn't tell me what the units are, so I have to leave it like that. And the area, by the way, you should remember the area is a half AB sine C. Probably not quite so nice, this. So half times the 5 times the 8 times the angle, sine of the angle, which was pi by 3. Sine of pi by 3 is not quite so nice, so if you type it in, you'll get 10 root 3. And I run out of time, so I'm just writing it. You could get that as a decimal as well. So that's what we're looking at. If you draw polar curves on your calculator, on this black calculator, you can just press. Well, first of all, we've already put it in polar, and then you just use the y equals button, and you type in. When you press, if it's in polar, it will come up with an R, probably with an R1. So 2 plus cos theta are what I want to type in. Now, again, you'll notice here there is a table button, and also a table set here. So using these, we can type them in. If you're not sure how to do it, have a play, and if you can't work it out, you might, for instance, the table set, you need to set the table going up in pi divided by 4. It needs to start at 0. Like, otherwise, you might find it's already set to that, but you might find it's not. And then we use the blue button and the table button, and you can get up this table. And what you're missing off the very last row is 6.28, which is 2 pi and 3. But when I do this, I can type this into my calculator, my black calculator, just by, rather than pressing table, I can just tell it to draw it. And if you draw it using the graph button, I reckon you get that. You might need to zoom in or zoom out to see it, but that's the graph that you should get. Now, that is one graph. Now, we theoretically need to be able to plot these, and just have a look at this. Look, this is when the angle is 0, the distance away is 3. Now, 0 is this direction, and 3 is there. When the angle is, well, no, it says 0.79. I know that's pi by 4. So that's pi by 4, 45 degrees. That's on this line here. It says 2.71. Now you can see that point there. When the angle is, I don't know, 3.14, that's pi, that's 180 degrees. It says the distance is 1 away. So in that direction, you can see the distance from here is 1 away. Let's pick another point, 4.71. I know this is 3 pi by 2. Now that's down this line, and it says it's 2 away. So that's my graph, and if you draw all those points, you'll get that graph. So what I'm interested in is what these graphs look like. Be aware that we've got to be careful of negative values. I might show you that more on the second video to this. But I want you to worry about these graphs. Here's another one. Type this into your calculator. And when I typed it in, I got this. Now notice, I reckon, by the way, on your calculator, this looks like this. And this is the negative R values I was telling you about. Now this is a danger to us. I will talk more about this next lesson. But I don't like this bit here. If you draw this bit here in your exam, you'll lose marks. That is what I should draw without that middle bit. So just be aware of here. So our calculator, in summary, is good, but it can cause us a problem. And I'll talk more about that in the next video. So I hope that helps, and we'll look at these a bit more. Good luck.